This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 3 of our series, Quantum Computing for Innovators. In this episode, titled Building a Basic Quantum Program, we're going to break down the essential components that make up a quantum program. Whether you're a seasoned coder or just starting out, you'll gain valuable insights that will help you navigate the exciting world of quantum programming. Let's dive in. IBM's quantum computers now run billions of tiny programs a day, yet most innovators have never written even one. You're in a meeting, someone says, "Let's use quantum," and the room goes quiet. In this episode, you'll break that silence by building your very first quantum program. The fastest way to stop quantum from being a buzzword in your strategy deck is to ship a tiny program yourself. Today, the barrier is shockingly low. With a browser and a free IBM account, you can push a 2-qubit circuit to a real device that lives in a data center hundreds of miles away. In Python, that's on the order of 10 to 15 lines of code. In Qiskit's Composer GUI, it's a handful of clicks. In this episode, you'll go from zero code to preparing a Bell state, a minimal circuit that already uses the same building blocks as production-scale algorithms. You'll see how a single gate choice changes measurable outcomes across 100-plus runs, and how simulators versus real hardware diverge. By the end, you won't just understand quantum programming, you'll have actually deployed it. Before you touch code, anchor what basic really means in this field. A minimal circuit for this episode will use just 2 qubits, 3 gates, and 1 measurement step, yet you'll control a system whose state lives in a 4-dimensional complex vector space. Frameworks like Qiskit or Cirq handle that math, but you still decide structure, which gates, in what order, on which qubits. Think of it as designing a 3-step workflow: initialize, transform, read out. Even this tiny workflow scales. Add only 8 more qubits and you're tracking 1024 complex amplitudes under the hood. To make this concrete, pick one stack and drive it end to end. Let's assume Qiskit, though the structure is similar in Cirq or Q#. You'll touch 4 moving parts: how many qubits you allocate, which operations you apply, where you measure, and how often you repeat the experiment. Start by installing the toolkit. Bash pip install Qiskit. In Python, you'll then import the building blocks and declare exactly 2 qubits and 2 classical bits. Python from Qiskit import quantum circuit. QC equals quantum circuit 2, 2. Line count so far? 2 lines of real code. Next, add your 3 operations that create the correlations you care about. Python qc.h 0, first gate on qubit 0. qc.cx 0, 1, second gate, control 0, target 1. qc.measure 0, 1, 0. Let's talk to successful. Python qc.cx 0, target 1. Second joys that completely real demonstratement increase educated fun state and what happens in stage to provide the rejective below that relating to kids measurement. Date again, you'll click 2 lines quietly. First of all, quantum circuit and C quantum circ, just 1 payload. Next, change the problem of qubits and included 1 quantum as well. Working to quantum many people of change. Next, pick 3 of well operations. Quantum circuit is second gate. Python qc.cx 0, target 1. Next, second gate control 0, target 1, qc.measure to quantum 0, target 1. Change the quantum is structures, but first is listed anywhere of the qubit. And this take a position to get other below is the qubit suggested by you filled. It's more structure, you can see what the living of quantum circuit. Step just 4 conclusion understand them to police the qubit 0. What they work ensure the gate is not only innovate, making someone who help up around it, You'll take it is listed and to find this position. Python, qc.qubits 0, target 1, qc.measure to 1, 0, 0, 1. Today, you'll begin to fill that quantum building to the program getting their information. Python, qc.qubits 0, target 1. Next, second gate, control 0, target 1, qc.measure to quantum 0, 1. Start by installing the toolkit. Bash pip install qskit 0, 1. That's the full quantum part, 5 short lines. Qiskit will now need 2 more ingredients, where to run, and how many repetitions, shots, you want. For rapid iteration, use a local state vector simulator. It calculates all 4 amplitudes exactly. Python, from Qiskit air, import air backend. Air, get.air simulator, job equals, backend.run, qc, shots equals 1024, result equals job.result. Print, result get counts. On a laptop with 16 gigabytes of RAM, this scales comfortably up to about 32 qubits. Beyond that, memory demands explode because the state has 2,000 complex numbers. At 2 qubits, you're only tracking 4. At 32, it's over 4 billion. Run this once and you should see counts close to text 00, 520, 11, 504. On a simulator, the distribution will hover around 50-50. Nothing else. No 0-1, no 10, if everything is wired correctly. Now switch to a cloud backend. In IBM's UI, you'll pick a real device and often be capped around 100 to 200 shots per job on the free tier. With 100 shots, perfect 50-50 becomes noisy. You might see 4700 and 5311. You may also see a couple of 0-1 or 10 events, thanks to gate and readout errors. Today, a well-calibrated single-qubit operation fails about once in 1,000 uses. Long-term fault-tolerant systems will need roughly 10 times better. From an innovation perspective, the most important thing you just learned is not the syntax. It's that you can express a complete Bell state experiment in under 15 lines, push it to industrial hardware shared with thousands of users, and directly observe hardware limitations that will shape product timelines. Think like a product team running A/B tests at microscopic scale. Once you have your basic Bell experiment working, the real learning comes from controlled tweaks and the numbers they produce. Example 1. Replace the Hadamard on qubit 0 with a poly X, keep everything else the same, and run 1,000 shots on the simulator. Log the counts, then switch back to the Hadamard and repeat. You've now run 2 feature variants differing by 1 line of code, each backed by 1,000 data points. Example 2. Keep the circuit fixed but vary shots. 50, 200, 1,000 on the same backend. Plot how the empirical probabilities converge. For many business-relevant use cases, you'll see that below 200 shots, your estimates can swing by 10 to 15%, which matters if you're optimizing costs or risk. Example 3. Run the same 2-qubit experiment on 3 different IBM devices in one day. Record queue time, seconds, job limit, and error-induced wrong outcomes. You're now doing primitive vendor benchmarking. Quantum literacy will soon matter far beyond R&D teams. As vendors expose higher-level APIs, non-specialists will call pre-built primitives, prepare 4-qubit GHZ, run QAOA depth 3 without touching circuits. Expect early APIs for portfolio optimization, route planning, and energy scheduling where you tune a handful of parameters, not gates. A practical target: be comfortable editing 20 to 50 line examples and reading job metadata, latency, queue depth, device ID, within 3 months. Next, push beyond toy demos. Add a third qubit and a second CX, then compare counts from 128 versus 4,096 shots. Note how rare outcomes stabilize. Time a full workflow. Edit, submit, receive results from 3 devices, and log total minutes. Within 30 days, aim to have 5 such experiments saved in Git so your team can replay and extend them. Start with this tiny habit. When you sit down at your computer each day, type a single line of quantum code that creates a 1-qubit circuit. For example, QC equals quantum circuit 1. Then, add just one more line to put a Hadamard gate on that qubit, like QC.H0, and stop there. No pressure to run or understand anything yet. If you feel curious, quickly print the circuit, print QC, and just look at the diagram for a few seconds, noticing how your Hello World quantum program is taking shape. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!